All right, today we're jumping into something really wild. It's a paper from theoretical physics that basically takes what we thought we knew about one of the weirdest things in the universe and turns it on its head.
So let's start with a big question. Have you ever looked at, say, a snowflake or a crystal? You see these perfect, repeating patterns, right? And a lot of physics is like that. It's all about finding these beautiful, orderly rules for the universe. But what if that's not the whole picture? What if all that perfect order is, well, kind of an illusion? What if our rulebook is missing a key chapter? Okay, so before we can talk about breaking the rules, we've got to understand the rules in the first place. So let's dive into the established science of this incredibly bizarre quantum state called superconductivity. So, what is a superconductor? Well, it's got two kind of superhero properties. First, you cool it down enough and boom, it conducts electricity with zero resistance. I mean, zero. That's perfect efficiency. And second, it actively kicks magnetic fields out, just pushes them away. It's called the Meissner effect, and it's like having a perfect magnetic shield. Now, for a long, long time, our main guide for understanding all this has been something called the Ginzburg-Landau theory. You can think of it as the official rule book for superconductors. And look, it's been insanely successful at explaining how they work on a big scale. It's really been the bedrock of our understanding. But, like any foundation, it's got some cracks. And this is where we get to the heart of the problem. That powerful Ginzburg-Landau theory? It has one major blind spot. See, it's built on the idea that everything is local. It assumes particles only react to what's happening to their immediate neighbors. Here's a good way to think about it. Imagine you're in a huge, packed crowd. A local interaction is simple. The person right next to you pushes you, so you move. Easy. But now imagine a non-local interaction. A huge wave of motion starts way over on the other side of the crowd. Nobody from over there is touching you, but you feel that ripple coming through, and you start swaying with it anyway. That's non-locality. You're reacting to something happening far, far away. And this is the key takeaway, right? The classic theory we've been using for decades is fundamentally local. It's all about those neighbor-to-neighbor shoves. It has absolutely no way to deal with the idea that a particle over here might be feeling what's happening way over there. That's the blind spot we're talking about. So that brings us to the paper at the center of all this. What it does is propose a really clever way to upgrade that old rule book, to give it a new pair of glasses so it can finally see these long-range, non-local effects. And just so you know where this is coming from, the work we're digging into was published back in 2022 in a journal called Physica B, Condensed Matter, and it's a real deep dive that suggests a huge update to how we think about superconductors. So what's their big idea? The authors created a new mathematical tool called a non-local momentum operator. Now that sounds complicated, I know, but the best way to think about it is like a software update. They're not tossing out the old theory, not at all. They're just installing a patch that gives it a brand new feature, the ability to see and calculate these weird long-distance interactions. And here's where things get really fun. Because once you install that software update, the theory starts spitting out some seriously bizarre, really exciting new predictions. The physics just gets, it gets weird, and it gets weird fast. All of a sudden, the model is predicting all this new stuff, like the size of the electron pairs that make superconductivity work. Turns out that can change. Particles can get trapped in ways we never thought possible. And those neat, perfect patterns of magnetic fields, forget about it. They become messy and chaotic. But the biggest one, the real kicker, is that the theory predicts a whole new class of material. Yeah, the authors themselves point to the craziest prediction of all, something they call a type 3 superconductor. And I love this. In the paper, they actually call its main feature a weird property. You know, when a physicist writes weird property in a formal paper, that's their version of screaming with excitement. So what makes it so weird? Okay, remember how a normal superconductor is like a perfect shield that pushes magnetic fields out? Well, a type 3 superconductor would do the exact opposite. It would actually create an opposing magnetic field on the inside. It's like a magnetic anti-shield, something that physicists pretty much thought was impossible. So let's step back for a second. What does all this mean for the big picture, for how we see the universe? Well, this whole idea of non-locality really makes us rethink what order even means. See, the old local theory predicted something very neat and tidy.
It said that when a magnetic field gets into a superconductor, it forms a perfect grid of little energy whirlpools. The best way to picture it is like a perfectly planted orchard, where every single tree is in a perfect, predictable row.
But this new, non-local theory, it throws that idea out the window. It says all those long-distance interactions will mess up that perfect grid. They'll deform it, creating a messy, non-repeating, more organic pattern. So that perfect orchard is gone, and what you have instead is a wild, natural forest. The patterns are still there, but they're way more complex and a whole lot less predictable.
And that's the thought I want to leave you with. Look, superconductivity is just one corner of physics, right? So if adding this idea of seeing from a distance can so radically change our picture here, it makes you wonder, doesn't it? What other fundamental laws of our universe might look completely different if we started to account for the strange physics of action at a distance?